Episode 6, titled Statistical Foundations, Populations, Samples, Parameters, and Estimates, the goal is to make sample versus population thinking feel automatic, because DataX questions often hinge on whether you can tell what is being measured and what can legitimately be inferred.
In real analytics work, you rarely see the full population, so you make decisions using samples, and the exam rewards the learner who understands what that implies about uncertainty and risk.
This is not about becoming a mathematician, but about building the kind of judgment that prevents you from making confident claims from thin evidence. When you hear a scenario, you want to be able to say quietly and quickly, "This is the population, this is the sample, and this is what we can estimate," without drifting into assumptions. That single framing step will protect you from many distractors that treat limited data as if it were complete truth.
Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A lot of exam confusion comes from mixing up closely related terms, so the next step is to distinguish parameter, statistic, estimator, and estimate with clean meanings. A parameter is a true value about a population, like a population mean or a population proportion, and it is usually unknown because you do not observe every member of the population. A statistic is a value computed from a sample, like a sample mean or a sample proportion, and it is what you can actually calculate from the data you have. An estimator is a rule or method for producing a statistic that targets a parameter, such as using the sample mean as an estimator of the population mean. An estimate is the specific value you got from applying that estimator to your sample, meaning it is the numerical result you will report or use in a decision. When you keep these distinctions straight, it becomes much easier to answer questions that ask what can be known, what can be inferred, and what is merely observed in one snapshot. Sampling error is another term that causes trouble, because people hear the word error and assume something went wrong. Sampling error is not a mistake. It is natural variation that occurs because a sample is only one possible subset of the population. If you took a different sample, even with the same method, you would almost certainly get a slightly different statistic, and that difference is the sampling error in action. The exam may describe two samples producing different results and then ask what explains the difference. And the correct reasoning is often that variation is expected, not that someone made a bad calculation. This matters because professionals who treat natural variation as failure end up overreacting, changing processes too quickly, or losing trust in valid measurements. The DataX mindset is to expect sampling error, quantify it when possible, and make decisions that respect the uncertainty it represents.
Sample size connects directly to uncertainty, and the exam often tests this relationship in conceptual form, even when it does not require heavy arithmetic. In general terms, larger samples tend to reduce uncertainty because they average out random variation, while smaller samples tend to produce wider swings from one sample to the next. One practical way the exam may express this is through confidence intervals, which are ranges that reflect how uncertain an estimate is, where larger samples often lead to narrower intervals. You do not need to treat this as a formula exercise to get the main idea right. More data usually means a more stable estimate, assuming the sampling method is sound. A common trap is assuming that a small sample with a dramatic result is more meaningful than a large sample with a moderate result, because dramatic results feel persuasive. DataX rewards the learner who asks, "How much uncertainty is implied here?" and who chooses answers that acknowledge interval width and stability, rather than leaning on the emotional appeal of a single point value.
Bias is different from sampling error, and the exam expects you to understand that difference because bias creates consistent distortion rather than random variation. Selection bias happens when the sample is not representative of the population you intend to understand, such as only sampling from a subgroup that is easier to reach or more likely to respond. Measurement bias happens when the instrument or process used to collect data systematically skews results, such as a sensor that reads high, a survey question that leads respondents, or a logging pipeline that drops certain events. Survivorship bias happens when you only observe what remains after a filtering process, such as only analyzing successful cases while ignoring those that failed and disappeared from the dataset. The exam often embeds these biases in scenario language, and the correct answer is frequently the one that identifies how the data collection process distorted the picture. When you learn to separate random sampling variation from systematic bias, you will avoid the trap of treating a biased dataset as if it could be fixed simply by collecting a slightly larger sample of the same flawed type. Because exam scenarios can be wordy, you need practice spotting population definitions inside messy wording, and this is where analyst-style reading matters. The population is the full set you care about, and the scenario may describe it in business terms, like all customers, all transactions, all devices, or all claims within a time window. The sample is what you actually observed, which might be a subset like customers who responded to a campaign, transactions above a threshold, devices reporting telemetry, or claims processed by one system. A common distractor is to treat the sample as the population, especially when the sample is described with confident language like the dataset, which sounds complete even when it is not. The exam will often ask what you can conclude, and the correct conclusion depends on whether your sample truly represents the population you want to talk about. When you train yourself to identify population and sample explicitly, you make it much harder for the question to trick you into overgeneralizing.
Summary measures become important when distributions are skewed, because skew changes what typical looks like and what measure best communicates it.
If a distribution has a long tail, a few extreme values can pull the mean away from what most observations look like.
In those cases, measures like the median can better represent the central tendency experienced by a typical member of the sample. The exam may describe income, response times, transaction amounts, or error counts, which often have skewed distributions, and then ask which summary is most appropriate.
The best answer is usually the one that reflects robustness to outliers and alignment with the decision, rather than the one that is most familiar.
This is not about declaring one measure superior in all cases, but about choosing the measure that matches the behavior of the data.
DataX rewards the learner who recognizes skew as a signal to be cautious with averages that can be distorted.
It also helps to contrast mean, median, and mode in terms of how they behave under different data patterns, because the exam can test this through scenario clues.
The mean is sensitive to extreme values, which makes it useful when you want that sensitivity, but risky when extreme values are rare noise.
The median is the middle value, which makes it more robust for skewed data or when outliers would misrepresent what is typical.
The mode is the most frequent value, which can be useful for categorical data or when you care about the most common outcome, but it can be misleading if the distribution has multiple peaks or if the most frequent value is not representative of the overall spread.
In practical terms, the question is often asking, what does typical mean here? And the correct choice depends on whether typical means average magnitude, middle position, or most common category.
When you connect the measure to the behavior of the data, you avoid picking a definition by rote and instead pick a statistic that fits the scenario.
Spread matters as much as center, which is why variance and standard deviation show up frequently as quick ways to describe how dispersed values are.
Variance captures the average squared distance from the mean, which makes it mathematically convenient, while standard deviation is the square root of variance and is often easier to interpret because it is in the same units as the original data.
The exam may not demand calculation, but it will test whether you understand that higher standard deviation implies more variability and less predictability around the central measure.
In scenario terms, a process with a stable mean but high spread can still be unreliable because outcomes vary widely from case to case. Conversely, a moderate mean with low spread can be more dependable in operations because performance is consistent. DataX questions often reward recognizing that consistency is a form of quality, and spread is one of the clearest signals of consistency. Outliers deserve careful interpretation because they can represent signals, errors, or rare events, and the correct response depends on which is most plausible in the scenario. Some outliers are data errors, like logging glitches, unit mistakes, duplicate records, or corrupted entries, and those should be investigated and corrected because they distort analysis. Some outliers are true rare events, like fraud, faults, spikes in traffic, or unusual but valid behaviors, and those may be exactly what you are trying to detect. Some outliers are signals of drift or change, where the system's behavior is shifting, and the outliers are early warnings rather than random noise. The exam often embeds hints, such as a new deployment, a system change, or a reporting gap, and those hints guide whether outliers should be treated as suspect measurements or meaningful events. A common distractor is to remove outliers automatically without considering the objective, which can destroy the very signal a detection or risk-focused task needs.
Standard error is a concept that helps connect sampling to stability, and the exam may test it as an interpretation rather than as a computation.
Standard error reflects how much a statistic like a sample mean would vary across repeated samples, and it is a way of describing estimate stability.
A smaller standard error implies that the estimate is more stable from sample to sample, which usually happens with larger effective sample sizes and more consistent data.
A larger standard error implies that the estimate is more sensitive to which particular observations you happen to sample, which means you should be more cautious about making strong claims. This concept is closely related to confidence intervals because standard error often influences how wide an interval is for a given level of confidence. In exam language, if you see references to stability, uncertainty, or how reliable an estimate is, standard error thinking is often the underlying idea. When you can connect stability to sample characteristics, you make better judgment calls about what conclusions are defensible. Sampling logic becomes especially important when classes are imbalanced and outcomes are rare, because a simple random sample can hide the very thing you care about. If the event of interest is rare, a sample may include very few positive cases, which makes estimates noisy and can mislead both evaluation and model training. The exam may describe rare outcomes like failures, fraud, or anomalies, and then ask what sampling or evaluation approach makes sense, which is where you must recognize that imbalance changes what representative and informative mean. In these scenarios, stratified sampling can help ensure that important groups or classes are present in both training and evaluation partitions, preserving meaningful comparisons. Oversampling can increase exposure to rare cases in training, but it must be handled carefully so you do not leak information across partitions or create unrealistic evaluation results. DataX rewards reasoning that respects rarity and class balance, because naive sampling can produce high accuracy while failing at the real objective of catching rare but costly events. A useful memory anchor for all of this is to hold the idea that population truth is the destination, sample snapshot is what you have, and estimate bridge is how you connect them responsibly. The population truth is what you would like to know, such as the real average, the real rate, or the real relationship in the full group you care about.
The sample snapshot is a limited view, shaped by how you collected data and by the random variation of which cases you happen to observe. The estimate is the bridge, and it is only as trustworthy as the sampling method, the absence of bias, and the stability implied by sample size and variability.
When you remember that bridge metaphor, you avoid treating a sample statistic as absolute truth, and you also avoid treating uncertainty as paralysis.
The exam rewards balanced reasoning, where you respect uncertainty but still make the best choice given the information available.
To conclude Episode 6, it helps to restate the key terms in your own words and then do a quick self-quiz using 3 examples, because that converts vocabulary into working judgment. You want to be able to identify a population, identify a sample, name a parameter you care about, name the statistic you can compute, and recognize whether sampling error or bias is the bigger threat in the scenario. You also want to recognize when skew suggests using a median instead of a mean, when spread matters for reliability, and when outliers should be investigated rather than ignored.
When you practice these examples aloud, you will notice whether you are slipping into assumptions, such as treating a convenient dataset as the full population, or treating a single estimate as a permanent fact. Keep the self-quiz focused on interpreting scenarios, because DataX is measuring whether you can reason under realistic constraints, not whether you can recite definitions without context.
If you can do that consistently, you will find that many exam questions become easier because you are no longer guessing about what the numbers mean.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.